Hello, everyone. This will be well, it's kind of a test to review part two, but it's also, I want to clear up that problem from class that we went over the other day that I don't feel like we did a very good job on. So, what actually happened with this problem is you see these values that we had here? Let me just make sure you can see what I'm saying. Um, yep, you can. Okay. Whoops. So, let's just take a look at this problem. Um, yeah, so what happens when I click this? The numbers randomize. So this is the problem we had in class. We were actually getting the right answer. It had just changed the numbers on us when I showed the completed problem. So I just want to go through and very thoroughly and completely um, explain what's going on with this problem because I don't feel like we did very good with that in class the other day. So let's take this back off and I'll show you exactly what's going on. And I'm also gonna bring up, yeah, something to write on. Okay, so, so what's the relevant information here? So can you see that? Yeah, okay. So the relevant information is that the probability that that the officer gets it right, that is, in this stated, that is 80%. Or 0.8. Um, this is not stated as a false positive or a false negative. This means we get it right 80% of the time. And I think that's what the confusing part about this problem for me is that the chance of a false positive is the same as the chance of a false negative, which is very rare, definitely with medical tests. And I don't know, I'd like to see some empirical data on this, frankly. Okay, so what do we have here? We also have that the probability that you are intoxicated, um, that is 21%, 0.21. And we have, oh, that's all we have. All right, so let's look at what a tree would look like for this. And we're going to get into a little fact about independence when you're looking at trees. So either you're intoxicated or you're not. Um, 0.21 are intoxicated, and 0.79 are not, right? We add those up. That's a 0, and 3, and 1, and 2, and 7 is 1, so we're good to go. Okay. Now, we also, on each of these branches, have a branch. We can be detained or we can not be detained. And the trick for this is the phrase, um, what is the phrase here? Um, Trained officers can make the right decision 80% of the time. So if you are intoxicated, the right decision would be detaining someone. If you are not intoxicated, then the right decision would be not detaining someone. And so here's what I'm talking about, right? The false positive, so you were detained, let me highlight. So you were detained, but you were not drunk. That is the same as the false negative rate over here. You were drunk, but you were not detained, right? So false positive, false negative there. Positive equals false negative. So that's a little bit unusual. Now the first question says, suppose that you have not been drinking. What's the probability that a statistics student is detained for further testing? So for A, we could write that as the probability that you are detained given that you have not been drinking. But what I want you to notice here is that when I set this up, so probability D, detained but not drinking, over probability that you have been not drinking at all. What do you notice about all the not drinking? They're all from the same branch, right? So when I fill this in, what I'll get is 0.79 times 0.2, over the same number, 0.79 times 0.2, plus 0.79 times 0.8. And when you work this out, what you get is 0.79 times 0.2 divided by, factoring out a 0.79, 0.2 plus 0.8. And so what this comes out to be is these will cancel out, and I'll get 0.2 over 1. So what we found there is we found that probability D, given that you are not intoxicated, is the same as the probability of making the right decision, of making the wrong decision, excuse me. And that is probability of detained when not intoxicated, right? Probability of making a mistake. Another way to think about this is probability of a mistake would be 1 minus probability of get it right, which would be 1 minus 0.8, which is 0.2. So that's another way to think about it. You can either do the conceptually thing like, well, they told us that the officers get it right 0.8, 80% of the time, therefore they must get it wrong 20% of the time. And so if you are not intoxicated 20% of the time, you'll be detained. That's kind of the conceptual way to think about it. But notice here, if you fill this in and you don't screw yourself up by hitting that show completed problem button and randomizing your numbers again, you will recover probability of being detained incorrectly, which is 0.2. So that's an example where we did kind of, we discovered that we had an independent probability there. All right, so that's part A. Let's just keep going with this though. So what am I going to put here? Let's see. What am I going to put here? I'm going to put 0.2 there. 0.2. All right, so you saw it, right? We can do it. We've done it. The only thing that screwed us up was hitting the show completed problem button up above. Okay, so what is the probability that any given driver will be detained? So this is just a matter of adding up the ways that you can be detained. So let's look up here. Ways to be detained are you're not intoxicated, but you did get detained, and you are, and you did, right? So that's an or. That's probability detained looks like this. It looks like probability not drunk and detained plus probability of drunk and detained. Those are our two options for getting the total probability of being detained. This one is 0.79 times 0.2. And this one is 0.21 for being drunk, and 0.8 for the probability of being detained when drunk. I borrowed somebody's office to do this problem, so I seem to be without a calculator at the moment. Let me just open Desmos real quick. Okay, so 0.79, show my parentheses, 0.79 times 0.2 plus 0.21 times 0.8. So 0.326. So popping back over to my homework, 0.326. Excellent. Thank you, Pearson. So we can do it, right? I'm really sorry this got so confusing in class the other day, but it didn't have to do with the problem, and it didn't have to do with our method. It happened to do with me forgetting that clicking this button randomizes the numbers. Okay, so those two weren't actually a Bayes rule, right? They were more of a what's the word? Well, there's just sort of more figuring out what branches of the tree relate, right? And we notice something there, right? It's independent. The probabilities are independent if you're pulling all your probabilities from the same first branch, right? So when we were asking about not being intoxicated, detained and not intoxicated, we're all the bottom, right? The bottom of this equation pulled numbers only from the non-intoxicated branch, and that's why we got independence. So that's a third way to think about independence, I guess. Okay, so now we want to know probability that a driver who is detained has actually been drinking. So what's the chance that you've been drinking given that you were detained? Um, well, let's just naively set that up. Intoxicated and detained divided by all the ways to be detained, right? Okay. And what we see here is that the ways to be detained are on opposite first branches. So this is non-independent. That's what we're seeing here. And so the ways to be detained are um, so intoxicated 0.21 and detained 0.8 divided by the same thing 0.21 times 0.8 plus 0.79, so the chance that you were not drunk, times the chance that you were detained and not drunk, which is 0.2. And similarly, 21 times 0.8, oops, I don't like that, divided by 0.21 times 0.8 plus 0.79 times, oops, times 0.2. So that's a 0.515. 0.515. That's surprising to anybody? Probability that you have been drinking. That's only 50%, even though they get right 80% of the time. Interesting. So one more to go. What's the probability that you'll be released when you actually have been drinking? All right. So probability that you're not detained. Whoops. Let me pull QuickTime back up so you can see. Oh crap, creepy. All right, here we are. So probability that you were not detained given that you were given that you had been drinking. Okay, let's check that out. That's going to look like, well, probability that you were not detained, but you were drinking, divided by all the ways to be drinking, right? Well, let's look back at our tree. This is another case where I'm pulling only probabilities off this branch, right? So this is another independent, right? This is the same thing as probability of a mistake again. Uh-oh. Could have sworn. Probability that a driver who was released had actually been drinking. Okay. Okay. So I read that backwards, right? Um, I'm just going to read that out. Yeah, there we go. I read that backwards. Probability. So what does that say? So we know the driver was released. So this is given, not detained. We want to know what's the probability that you had been drinking. Okay. Now this is non-independent. Now we're pulling from opposite sides of the branches because our top is going to be I and detained, but our bottom is going to be, or sorry, and not detained, but the bottom is going to be probability not detained. If we look back at our tree, we see not detained appears on both sides of the tree. So this comes out to be, so probability drinking 0.21 times probability not detained 0.2 divided by that same thing, 0.21 times 0.2 plus, so chance you haven't been drinking and were not detained, so that's 0.79 times 0.8. And hopping over to trusty Desmos, I'm actually just going to reuse this calculation here. Because all I have to change is the 0.8 and the 0.2 here. So we're just using the opposite branches there. And that comes out to 0.249. All right, hop back over here. 0.249. Oh, 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 oh. So the probability that a driver who was released had actually been drinking. So check our Desmos. Right here. That should be a 0.2, not a 0.8. So 0.062. That seems a little bit better. 0.062. Sorry about those wrong answers, guys. 0.062. There we go. Okay, so I hope that was a little bit clearer. The idea here is be very, very careful. Be very, very careful with how you set up those probabilities. It's easy to mess up, so it's better to double check. Like up here, where I mean, you just can't trust the order of the statement. I guess that's what I'm trying to say here. You can't trust the order of the statement. You have to really parse the language to figure out which one is given and which one is not. And if you just do this expression every time and trust yourself, like we did here, you can see that you can recover independence or non-independence just from the properties of the tree and stuff like that. I'm out of time for making this video, unfortunately. I'm borrowing somebody's office to do this. So what I'm going to do is cut this off here, and I'll just have to make another one later on today. So that's your first one. I think for the next one, I'm going to add some probabilities as well as do at least another tree problem like this one or similar to this one. So I hope that helped everybody, and have a good day.